Have you ever watched the music fountain show and wondered how those beautiful water jets are engineered to dance in the air? Behind many of these designs lies one of the most important equations in fluid mechanics, Bernoulli's equation. This fundamental principle is used in countless real-world engineering applications, including fountain systems, pipelines, and hydraulic designs. Not surprisingly, Bernoulli's equation is also one of the most frequently tested concepts on the FE and PE engineering exams. In this video, we'll break down how Bernoulli's equation works and walk through a tricky example problem step by step to help you understand the physics behind these impressive water displays. Let's get started. Here we have a water fountain that shoots water from a 3-inch nozzle, and the water reaches a height of 10 feet. The nozzle is connected to a straight 6-inch water pipe. What would be the pressure of water 10 feet below the nozzle outlet? A common mistake is to directly write one single Bernoulli's equation from the highest point reached by the fountain water, point 3, to the location of interest, point 1. Let's analyze this equation to find out what the issue is. At point 3, the gauge pressure is 0 because water is in the atmosphere, receiving only pressure from the atmosphere. While this absolute pressure equals to the local atmospheric pressure, the corresponding gauge pressure is 0. If you are confused about the difference between absolute pressure and gauge pressure, click the link to watch one of my previous videos made for this topic. Also at point 3, the velocity would be 0 because water can rise up no more. But if you look at the right side of the Bernoulli's equation, we soon realize that both the pressure P1 and the velocity V1 at point 1 are unknown. It is mathematically impossible to solve two unknowns with one equation. Therefore, we need more work to be done. So here's the idea. How about we start with one Bernoulli's equation from point 3, then stop at point 2, which is at outlet of the nozzle. We will use the Bernoulli's equation to find the value of velocity at the outlet, V2. We will then write another Bernoulli's equation from the outlet point 2 towards the location of interest, point 1, for calculating the pressure there. The velocity calculated at point 2 can be used to determine the velocity at point 1 using the continuity equation Q equals V times A. And by doing this, we will have only one unknown left to be answered, and that is pressure P1. Now that we have analyzed the logic of our solution process, let's give it a try. We start with the turn-by-turn analysis of the first Bernoulli's equation, from point 3 to point 2. Water at both locations are in the atmosphere. Therefore, their gauge pressure, P3 and P2, would both be 0. As we previously discussed, the velocity at the highest point, point 3, is 0, so V3 equals 0. The difference between Z3 and Z2 is 10 feet. Only one unknown, V2, is in this equation, which means we can solve for this value directly. And here we have V2 equals 25.4 feet per second. Next, the continuity equation. We know that the discharge of volume flow rate, Q, is constant, regardless of the change in pipe size. So the products of velocity and the cross-section area at point 2 and point 1 are the same. Rearranging this relationship, we can find V1 as V2 multiplied by the ratio of A2 and A1. For a circular nozzle and a circular pipe, the ratio of cross-section areas equals to the squared ratio of diameters. Consequently, we have V1 equals 6.3 feet per second. And finally, let's substitute the values of V2 and V1 into the second Bernoulli's equation. Note that P2 is 0 as water at point 2, the outlet, is in the atmosphere. The difference between Z2 and Z1 is 10 feet. The specific weight of water, we can use 62.4 pound-force per cubic feet. It is very important to keep track of the units we use in this process. The pressure P1 is found to be 1210.7 pound-force per square foot. And that is PSF, not PSI. If the result needs to be in PSI, we will work on 1 unit conversion. And we have P1 equals 8.4 PSI. If you found this video helpful and want to learn more about civil engineering and professional engineering exams, like and share this video, subscribe to the channel, and comment below with the topics you would like me to cover in future videos. Thanks for watching, and I'll see you in the next one.